just a moment for everyone to be able to get on. If in the meantime, if you want to in the chat, share where you are coming from, that would be great. Pleased to have you here.
All right. Hello and welcome to today's webinar. My name is Dana Ollendyke and I'm the project manager for the Penn State Extension Energy team and also a member of the TOPCORP training team. I'm joined by my colleagues Dan Brockett and Tom Berezniak here at Penn State, who will be helping me co-host. We are very grateful to have Dr. Emami-Meybod here with us today to speak about boosting shale oil recovery. This webinar is hosted by TOPCORP, which is a consortium of universities that deliver oil and gas regulator training. Our consortium includes Penn State Extension, the Colorado School of Mines, and the University of Texas at Austin. TOPCORP's mission is to train regulatory oil and gas field inspectors and policy-making personnel, as well as provide technical knowledge, growth in professional networks, and an increase in participants' confidence. We train regulators in the US and Canada, and we continue to expand our curriculum to include offshore aspects of oil and gas operations. Here you will see a listing of all of our groups and businesses that help support TOPCORP. Thank you so much for your support, and we couldn't do this without you. Before we get started, I just want to mention some housekeeping items. Use the chat pod to introduce yourself and the Q&A pod to ask questions during the webinar. If there is time after the presentation, we will ask those questions of our presenter. This webinar is being recorded and you will receive an email in about 3 business days with a link to the recording. You can also visit the Top Energy Training website for past webinar information.
Oh, hey, thanks, Dana. It's my pleasure here to introduce our presenter for today. Came about from a great article in Penn State News that he did, and a lot of the research his team has done is pretty cutting edge. So we're really excited about this. Dr. Emami-Meybod is an associate professor of petroleum and natural gas engineering in the John and Willie Leone Family Department of Energy and Mineral Engineering here at Penn State University. He also serves as faculty associate in the EMS Energy Institute and holds the prestigious Dr. Charles H. Bowman and Lynn Holleran early career professorship. As director of the Subsurface Energy Recovery and Storage Joint Industry Partnership, Dr. Emami-Meybod leads cutting-edge research on enhanced hydrocarbon recovery and carbon sequestration in unconventional reservoirs, including innovative CO2 injection techniques that boost oil output while mitigating emissions. His work has been recognized by the American Chemical Society Petroleum Research Fund, and he's a leading voice in advancing U.S. energy security and sustainability. And without further ado, please welcome Dr. Emami-Meybod.
Thank you, Tom. Good afternoon, everyone. My name is Hamid Emami-Meybod, and I want to first thanks for the Penn State Extension for this opportunity. So for this talk, I thought to start at the beginning with some basics on shales and why they are important to us in terms of energy, right? And then I dive into how we can improve recovery factor, right? And also, if you want to use this shale formation for storage purposes, CO2 storage purposes, what are the things that we want to be mindful of? So shale reservoir, right? These are the reservoirs that are pretty much everywhere globally, right? And most of these shale formation are the source rock for the conventional reservoir we know as a typical oil and gas reservoirs, right? In United States, just based on the information in 2023, 2/3 of oil production and over 3/4 of the natural gas production are coming from this shale formation. So they are significant in terms of resources and energy security for United States. And I have to say, United States is by far well ahead of other countries in terms of hydrocarbon production from this formation. So there are 4 main shale basins in the United States that we get most of the oil production from. So this is for the shale oil production. For the gas, of course, there are different basins. These four are the Midland, Wolfcamp, Delaware Wolfcamp, Bakken, and Eagle Ford, right? And the amount of resources we are talking about among these four basins are over 1,300 billion barrels of oil, right? So considering the daily oil production that we have around 30 million barrels per day in the United States, right? These four basins are enough for the oil production for the same rate of daily rate for the next 260 years. So there are lots of oil within this formation. So, but how these formations are different from the typical conventional oil and gas reservoirs. So if you look at the sandstone formation, right, or carbonate even, when you look at the pore size, this is the pore in the rocks in the reservoir, right? When you want to look at the size of those pores, in the typical sandstone or conventional reservoir, we are talking about the average pore size being higher than 0.1 micron, right? But when it gets to the shale, this number is much smaller by 2 or 3 orders of magnitude. So we are talking about nanopores. Nanopores refers to the having pores in the rock that has the diameter of nanometer, right? They usually are less than 100 nanometers, right? And that would change a lot of things when it gets to producing from this formation, right? So then the issue with this tight or nanopore system is that you're not going to have easy production of hydrocarbon from these rocks. So thanks to the horizontal drilling and hydraulic fracturing technology, right? So we can produce a lot of oil from this formation. And the way it works is that with the horizontal drilling, you have larger access now to the same formation, right? And with fracking, you're creating more contact between your wellbore and the reservoir. So basically, we are, in order to compensate for the small pore size that we have, we are increasing the contact area between the well and formation to boost the production, right? So, but if you look at the production from a shale well, right? And this is a kind of well, a type well, which means like we can see how fast the production is dropping. In a year, this is for Eagle Ford in Texas, just over a year, right? You can see the production of oil for that well dropped from something that's higher than 700 barrels per day to something around 200 barrels per day. So you have significant drop of oil rate when it gets to this formation. Because initially you have high production rate because you have a lot of fracture that give you a lot of contact between the wellbore and reservoir. But that's good for initial production because you have a lot of oil close to the fracture system that you created. But then as oil needs to come from deeper into the formation to this fracture system, it takes time. Therefore, the production drops quickly, right? And production mainly is from the area that you have fracture there, so which we call it a stimulated reservoir volume, right? So the higher this volume is, the more production you're going to get, basically, over the life of the well. But if you look at all these four basins that I mentioned at the beginning, right? Look at, see how, compared to the amount of oil we have there, how much of it is going to be, we can produce just through primary production. Primary production means just drill the well, do the fracking, and let the oil come out, right? So depending on the basin, you can see anything between 5 to 12% of oil in place we can produce through primary production. That means around 90 to 95% of the oil, it still remain there, right? That's a significant amount of hydrocarbon, or oil in this case, left behind. And the question we have, can we do better? Can we increase this number of, let's say, 10% or 12% to 15%, to 20%? Because even small increase in the recovery factor, it means a lot of oil, additional oil being produced, because we are talking about huge amount of resources. So what are the options in terms of improving that recovery factor or producing additional oil? So injecting different fluids into a reservoir to produce more oil is nothing new. So we have been doing this for many years for typical or conventional reservoirs. And the way it usually works is that you can either inject water or polymer or surfactant or gas to push the oil from one well to another well. So you have an injection well, and then you have production well, and depending on what fluid you're using, there are different mechanisms involved to produce more oil, right? For example, if you have water, you can just inject it and do a push of oil to the production well, so it's water flooding, right? Whereas with gas, which we can say it can be methane as a gas or CO2 or nitrogen, there are different mechanisms involved because gas, some of them can be miscible in oil, and it's improved the recovery factor, not just by pushing it through other mechanisms, which I'm going to talk about later. So with water, polymer, or surfactant, if you want to do that, when it gets to now shale formation or unconventional reservoir, right, there are going to be issues. And the issue is the injectivity. We may not be able to push the injected fluid into the formation much because of extremely low permeability of this formation. And that low permeability, or permeability, just to clarify, permeability is basically a measure of fluid being able to flow through a rock, right? So when you have small pores, as I mentioned, 2 to 3 order of magnitude smaller than what we have in a typical reservoir. Therefore, your permeability, or the measure that we use for the fluid going through the rock, is going to be significantly smaller, right? So therefore, we are not going to be able to push oil by injecting, let's say, water. So one of the things has been worked very well with the unconventional, especially shale, is gas injection. And I'm talking about methane, CO2, or nitrogen, right? Let's talk about gas injection processes. There are 3 types of gas injection processes. You can inject gas continuously. You can inject gas with water, but change it, like you inject a slug of water, then gas, then water, then gas, right? Why we do water alternating gas injection? Because you can save on the amount of gas you need to inject, and also water provide a good mobility because gas can go through the system quickly, through the reservoir quickly. Or the third option is cyclic gas injection. I'm just going to quickly go through these 3, and I show you which one is going to be best for shale formation. With the continuous gas injection, right, the main issue is that when it gets to shale, due to low permeability of this formation, we are not able to push oil through from one injection well to the production well, right? With water alternating gas, although you need less gas and water has a good create a good mobility, the issue is, again, the water and clay in the shale formation, they're going to cause the issue of clay swelling, and damage the formation. But also, it's very hard to push oil by injecting water, again, due to low permeability. So among these 3 options of gas injection, cyclic gas injection has been proven to be a practical option for improving oil recovery from shales. So the cyclic gas injection process is based on a single well operation. So the way it works, you inject the gas. That gas could be CO2, methane, or nitrogen, or even C2, ethane, right? Or a mixture of ethane and methane. You inject a slug of gas, then you shut in the well and let the injected gas that's now is in the network of fracture to go into the matrix, to the rocks, right? Then after a soaking period, and that could be, depending on your design, could be a few days to a couple of or weeks or months. Then you start producing from the same well. You have a single well that you inject the gas into, you shut in, and then you start producing from the same well, right? So the injection phase is called Huff, when you are injecting gas, and the production phase is called Puff. During Puff, we are producing not only some extra oil, but also some of this gas we injected. So some of that's going to be reproduced, right? So this process, that's why it's called Huff and Puff, because you're injecting gas and then you are producing it. So for the rest of this presentation, I may refer to gas Huff and Puff, which means basically cyclic gas injection. So gas Huff and Puff has been implemented in many shale oil formation in the US. Many companies, they have data, although it's not being shared. Based on the limited data that are available, we know, for example, this is information from a pilot test of 4 wells in Eagle Ford, that over 210,000 barrels of additional oil was obtained from that one Huff and Puff pilot test, right? Which resulted in basically extra oil that's about uplift of 1.36 times of what we could have got from primary production, right? So that means basically about 36% additional oil. And if you consider that, and we use the same information and apply it to the other basins, right? One can say, okay, the primary recovery factor is between 5 to 12, but that number can be increased significantly. And if you compare for example, the information in this column, which is for incremental recovery due to, Huff and Puff with CO2, compared to what you got from primary, you can tell, for example, here you had about 37% additional oil compared to the initial primary production. Or in this case, if you compare the 7.6 billion barrel extra oil compared to what you got from primary production, you can tell is more than 50% of what you got from primary production, and so on. But in addition to producing more oil, what can you do is if you're using CO2 as your gas, you can keep some of the CO2 in the formation. And the estimate for just these 4 basins, for amount of CO2 that we potentially can store, is about 20 gigametric ton of CO2, right? So I'm going to talk a bit about CO2 storage part, and then we go talk about the work that we have done at Penn State. So that was for the 4 wells, is 20 gigaton of CO2 we can potentially store. But if you consider all other shales in the US, so we can have 25 gigaton of CO2 be stored. And that's basically replacing what we already produced from this formation. So when we produce oil from the shale formation, you're producing oil, maybe gas, and also water, right? So the volume that's now is emptied, right? You can assume you can put CO2 in place of those that you produce. And that's a big number. So just give you an idea, this is equivalent to, I believe, 2/3 of global emission in a year for CO2. But what are the challenges when you get to storing CO2? For a typical conventional reservoir, right, or aquifer, the challenges is, the monitoring of the CO2 plume, where it's going to be, right? The liability that associated with that, who is basically responsible for if the CO2 leaks, and of course the leakage, right? And injection wells and well integrity is part of that process, and you need to consider, if you're injecting CO2, it's going to cause if it's aquifer, the water to becoming acidic, and that's going to cause some corrosion around the wellbore. But when it gets to shale, in addition to these issues, right, since we are dealing with a complex rocks, more complex than a typical conventional well formation, then the things that we need to understand what's happening in the rock within the small pores if the CO2 is being injected into those rocks, right? And understanding of that is going to help us to answer the question of how we can basically permanently store CO2 in this shale formation. So speaking of the mechanism, let me put some kind of information about what are the typical mechanism helping for oil recovery when you inject CO2 or gas or like nitrogen in a Huff-n-Puff process. So there are generally 5 different mechanisms. I'm going to talk about the first 3: oil swelling, vaporization, and competitive fluid-solid interaction. And these are the things that happen within small pores in a shale rock, right? So with oil swelling, I have an experimental data here. What we see here, if you have, let's say, CO2 and mixed with oil, it's going to increase its volume, right? Because CO2 dissolved in the oil creates a single phase, and that single phase, it has higher volume than before. Therefore, the volume, the extra volume, right, needs to go somewhere. So if the CO2 gets to the oil in a small pores, it's going to push some of the oil out because it needs more volume, right? That's called oil swelling. The other mechanism is that when you inject CO2 in the gas phase, right, basically, it's going to extract some of the component in the oil. So you're going to have oil phase and gas phase, but then now that gas phase is going to be CO2 and some hydrocarbon molecules like C4, C5, right? So that process called vaporization. You have some molecules in the oil phase, now it's part of CO2. And then your gas phase now is CO2 and hydrocarbon. And when you produce from the well, when the gas phase being produced back, it not only has CO2, but also has other hydrocarbon. Another mechanism that helps for producing oil through the gas Huff-n-Puff process is competitive fluid-solid interaction. The fluid-solid interaction refers to interaction of the injected gas, in this case could be CO2 or methane, with the solid surfaces of your pore system, right? There is a attractive forces between certain molecules in a fluid and solid surfaces. So if you have a lot of organic matter in shale, so if you inject CO2, CO2 loves to stay around the solid surface of organic matter. Therefore, it's going to push out oil molecules that are around the pore surfaces, right? So that competitive fluid-solid interaction helps for CO2 to go and basically kick out the oil or hydrocarbon molecules from small pores. So there are several, when it gets to the shale, there are several things that we have to be mindful of, because we are looking at a system that has not only macropores. Macropores refers to the pores that are large in pore size. They are usually higher than 100 nanometers in pore size, like a typical reservoirs. They are mostly all basically the pore sizes are macropores. But in addition to macropores, we have nanopores. These are the pores with the average diameter less than 100 nanometers. But also we have fracture system, right? That means when we want to looking at how to, let's say, simulate the process of gas Huff-n-Puff in a shale formation, we need to consider all these 3 different media, right? So multi-continuum porous media is what is needed when you want to do a simulation of the gas Huff-n-Puff in shale, which is not the case necessarily for a typical conventional reservoir. The other things that we have to consider is a small pores means the transports of fluids within these pores are going to be now driven with different mechanism, right? So in a typical reservoir, everything is modeled based on viscous flow, meaning Darcy law. I mean, petroleum engineering field, everybody knows Darcy law because that's the only equation we use to relate pressure changes with production or rate. But when it gets to nanopore, you have to consider the other mechanism. including interaction of molecules and pore surfaces. So fluid transport mechanisms are important to be considered to have a more reliable modeling of your process. Another thing that you need to consider, again, when you're looking at the small pores, you're going to have the fluid properties to behave or show different behaviors than if it's in a bigger pores, right? So you have nano-confinement effect and also fluid wall interactions that affect on the fluid properties. This is density of oil, let's say, or density of your injected gas, CO2, viscosity of oil. All of them are going to be different because they are under confinement. So these three aspects are the one that at least we need to consider that are different compared to the traditional simulators that they don't consider nanopores, right? So what we did, we said, okay, let's develop a simulator. Penn State, we call it PennShale, that can be used for the simulation of the process of Huff-n-Puff, but considering all these three aspects of nanopores, right, that affects on phase behavior, affecting on the transport, but also multi-scale continuum. So our simulator basically kind of simplified the fracture network and that we have to plan our fractures, and we consider a block of matrix is connected to fracture, and basically we simulate this part and we say this is repeated throughout the system or reservoir, right? But within this block, we consider all the fluid mechanism, transport mechanism, and also thermodynamic that is relevant to nanopores. So I'm not going to go through the details of the model we developed, but basically what we did is to develop an in-house simulator that considered the effect of nanopores on phase behavior, transport of fluid within nanopores, and having different type of media, which is fracture, micropores, and nanopore. So I'm going to go now through some of the results we got, and starting with the parameters that's going to affect on this process of Huff-n-Puff, right? The first thing is that we look at seeing whether Huff-n-Puff is good for what type of oil, right? Is it going to be good if you're going with the black oil, volatile oil, gas condensate, or just gas, right? Wet gas, right? Because you still can use that for all this shale formation, but how much recovery we're going to get, additional recovery. So simple analysis we have done is just primary recovery factor for different gas, different hydrocarbon systems. So in this plot, what we have is ultimate recovery factor on the y-axis, and the x-axis is basically from left to right, we go from dry gas system to black oil. So it's getting heavier and heavier. And you can see there are two curves. These are a different bottom hole pressure, but both are showing the same trend. The primary recovery factor decreases with increasing the oil molecular weight or equivalent molecular weight. That means the heavier the oil, the primary production is going to be less. So therefore, if you want to apply gas Huff-n-Puff, you're going to have more upside potential if it's heavier oil rather than just gas or gas condition. The second parameter we looked at is the injection gas type. So I'm going to talk more about CO2, but we also use methane and nitrogen for Huff-n-Puff. Especially we're using methane way more than CO2 and nitrogen. Why? Because methane is what's produced from the oil formations, right? So it's much cheaper to re-inject the methane that's produced with your oil to do an EOR process of, let's say, methane Huff-n-Puff, right? But when we look at this comparison between these three gases, right? So what we have here is the plot of recovery factor versus time. So initially what we have is just primary production up to here. So after this time, now you can see there are some sort of stairs, right? Each of this bump represent one Huff-n-Puff cycle. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 cycles. So doing the 10 cycle for these 3 different gases, we can see after 10 cycles, CO2 is doing better than methane, than nitrogen. And we say, okay, why is that? The reason is that when you use CO2 is heavier than methane. And in terms of interaction with oil, it can bring out heavier oil components to the gas phase. And the gas phase is more mobile than oil phase. Therefore, when you produce from the wells, what you produce first is going to be more of gas. And if you have more heavier oil molecules or component in the gas phase, so you're producing more of them. Therefore, the recovery factor of CO2 is higher than methane. But still, methane also is giving you good recovery, especially if you want to look at the economical aspects of it. Methane could win this, right? Because CO2, you're going to have to be worried about few other things that you're not going to be worried about in the case of methane. When it gets to CO2, you have to be also, you have to consider the wellbore integrity, right? Because it can cause corrosion, right? And here's some numbers from the mechanical integrity test when different injection fluids were used. So CO2 usually shows that cause around 11% of a failure when it gets to wellbore integrity. And depending on the type of the gas you have for injection, right, you have to be mindful of the type of the corrosion-resistant alloy that you need for your casing and tubing, right? So that's something to be mindful of if you're doing a CO2 injection as compared to methane injection. The other thing is the CO2 source and transportation, right? With CO2, it's not everywhere, especially in its pure form, right? I know there are a lot of work on direct air capture of CO2. If that gets to the point that's economical and larger scale can be possible, then it's going to remove that hurdle. But as of now, also we have some pipelines in the US where you can move CO2 from usually it's a plant that the emission or the flue gas from there is more than 80 or 90% CO2, pure CO2 basically, that it makes sense to use them for EOR processes without too much of pre-processing. Because if your CO2 is not pure and then you have H2S, let's say, in it, then you have other issues, right? Because H2S is more corrosive and hazardous. The other things we looked at is primary production time. So, I mean, we don't do Huff-n-Puff right away when we produce oil from a fractured well. We wait. We produce like a primary production. It's going to take some time. But how long should we wait? So you can see here there are results of 4 different simulations. The first one is we waited 1 year of production, primary production, then it started the Huff-n-Puff, waited 3 years, waited 5 years, and waited 7 years. What we don't want to do is to do it quickly, right? Right after a year, if you start doing Huff-n-Puff, you're not really getting to the potential that Huff-n-Puff could have because you want to allow the wells to produce enough oil that you have some space there opened up for the injected CO2 to go there and mix with the oil and help production. For the same simulations, when we look at the CO2 recycling, and if you want to look at it from CO2 storage point of view, it's better to have longer primary production. So what we have here is y-axis is recycling ratio and the x-axis is time. So recycling ratio is the ratio of produced CO2 during puff over total injected CO2 during Huff, right? So If this gets to 100%, that means whatever you injected for Huff-n-Puff, you produce, right? So if you want to keep the CO2 down in the formation, you want this number to be small, right? The recycling, right? So if you waited longer primary production, so you can see this blue curve represent that longer primary production. So the ultimate recycling, CO2 recycling is about below 80%. It's still high, you are producing 80% of CO2, but as compared to the first year, which is about 90%, at least you kept 10% more CO2 downhole. But when it gets to the CO2 storage, right, and if our objective is to store more CO2, we have to change our strategy. Because so far, I mean, what we have done here is trying to increase the incremental recovery. But if you want to keep more CO2 down, you have to have different approach. Still same process. What are the processes that we can rely on for storing CO2? I mean, cyclic gas injection or CO2 injection is, of course, one. Basically, you produce oil first, then you do CO2 Huff-n-Puff, and then for the last cycle, you inject as much as CO2 you can. As opposed to continuous injection, that when you produce oil, then just start injecting CO2 as much as you can, and then shutting the valve, and then don't go around it, right? Well, let's compare the result of these two scenarios. If you inject continuously, or if you do cyclic gas injection. So here on the top, we have the amount of CO2 produced or stored in the shale formation that we simulated. If you use continuous approach, is the blue curve, right? So you can see over 6 years, let's say, you store about 60 times, 60 M ton of CO2 for that simulation we have done. But if you do Huff-n-Puff, because you produce the CO2 again during puff, it goes ups and down, ups and down, ups and down. But because you're producing also some oil, you're opening more space for the next cycle that you have CO2 injected to go there. So after 6 years, and you have, let's say, 1, 2, 3, 4, 5, 6 cycles, you can see the amount of CO2 you could keep there is going to be much higher, so almost twice, right? But what happens when we inject CO2 like this process? The key is that when you do cycling CO2 injection or CO2 Huff-n-Puff, initially you may not have CO2 staying in all the big pores because you're also producing. But over a long period of time, right, what happens is that the CO2 that is in the macropores, the bigger pores, the volume of it is going to go down because it's going to move to the smaller pores, right? And that's actually very important when it gets to the process of cyclic CO2 injection, because you're opening up more or producing more oil from maybe macropores, and then in the next cycle you're injecting or putting more CO2 in those pores. So basically, what we found is the cyclic gas injection also helps for storing more CO2 than just continuous injection. But there are so many different parameters that affect on the cyclic gas injection, or basically CO2 Huff-n-Puff, from the reservoir properties all the way to operational. So you look at the parameters here, there are a lot of operational variables that we can control that affect on the process of CO2 Huff-n-Puff, including how long the primary production should be, number of cycles, huff time, soak time, puff time, bottom hole pressure, injection rate. This is the CO2 injection rate. So we thought, okay, now we have a simulator that can be basically more reliable in terms of simulating the process of CO2 Huff-n-Puff. Why not we come up with a workflow that we can optimize this process of CO2 Huff-n-Puff to increase the production, and basically also we can find where are the good target blocks for the gas Huff-n-Puff if you incorporate the reservoir properties to these operational parameters. So the workflow we developed is basically follows 4 different steps. One is the first step is to basically identify the reservoir properties and the parameters that we want to consider in optimization. And these are the operational parameters and reservoir parameters that are listed here. Then with the PennShale simulator we can run simulations, but before we running simulation, we want to calibrate our PennShale model with the actual field data, which we did. And this history match guys kind of give us a more confidence on what we're going to do in terms of generating simulation data set. Then using this the calibrated model, we start generating a lot of data. So basically we changed operational variables and fluid and reservoir properties to come up with different scenarios in which we have recovery factor calculated using the simulator. Then we use those set of training, set of simulation results to do training of a model, a proxy model. This is similar to, this is a smaller scale machine learning basically, or data analytics, that you have a lot of data sets, and then use that to train a proxy model that's going to substitute your simulator. And then we use a method of optimization to basically figure out which set of parameters would give us the best outcome in terms of recovery factor, if that's an objective. So I'm going to go through the implementation of the workflow we developed, and I picked 3 scenarios, right? So there are 11 variables that we said we're going to change. If we have like these variables from operator, right, then we can basically do optimization. What are these variables? Number of cycle for Huff-n-Puff, Huff time, Puff time, soak time, primary production time, bottom hole pressure, injection rate, reservoir depths, matrix average, pore diameter, this is pore sizes, fracture spacing, and oil type. So in scenario 1, we just want to focus on these first 3 parameters, which are related to Huff-n-Puff process itself, the timing of it, and how many cycles. In scenario 2, now we're going to add 4 more parameters that includes basically primary production time, bottom hole pressure, injection rate, as well as the soak time. This is going to help us to basically do optimization of Eagle Ford Shale, because for Eagle Ford Shale, the data we know what reservoir we have, we knew what are the reservoir properties, right? And we just said, okay, let's just optimize what would be the best combination of these parameters for maximizing oil recovery. And if you want to look at or find a target block for CO2 Huff-n-Puff, then we can consider all 11 of them. And I'm going to go through the result of all these 3 scenarios. In the scenario 1, we change the number of cycle, Huff time, and Puff time in this manner. So the range of the changes are shown here. The number of cycle from 0 to 10, number of the time of the Huff, anything between 30 to 180 days, Puff time, anything between 30 to 360 about the year, right? And this was, so, and we had a base case, right? This is recovery factor versus time. A base case is from the data we had from a paper for the Eagle Ford, that they did this kind of Huff-n-Puff. We said, okay, this is the base case, right, for the pilot test that was done and the data are published. Then we said, okay, if we just change these 3 parameters and do optimization, can we do better? And we found we can do better just by changing the number of cycle, Huff time, and Puff time. So compared to what we had in the base case, which is 5 number of cycle, 90 days of Huff times, and 180 days of Puff time, to these numbers, the optimum numbers here, we can see the recovery factor increased just by changing 3 parameters. Then we said, okay, in scenario 2, let's add these 4 more parameters and see whether we can improve that recovery factor Here again, the base case. This is the scenario 1, which we did optimization. And then if we can allow the other parameters change, especially bottom hole pressure and injection rate, because they affect significantly on even your primary production, right? That's why this moves up, because you change the bottom hole pressure. Therefore, you can get to much higher production, right? And in scenario 3, we change all these 11 parameters. We even have different type of oil, volatile versus black oil. And what we found is that we can get to much higher recovery factor if we find an optimum set of parameters for all these 11 parameters listed here. And this is basically what you can see here. For this example, the recovery factor was about 6%. It moved all the way up to about 14%. This is 8% additional recovery factor. So to conclude, gas Huff-n-Puff is a practical and effective enhanced oil recovery method for shale oil reservoir, right? But things to be mindful of, there are ER mechanisms that helps the process and producing more oil, including oil soiling, vaporization of the hydrocarbon component to the gas phase, and competitive fluid-solid interaction. The type of injected gas can affect under recovery. The duration of primary time would affect under recovery factor. And in terms of Huff-n-Puff, you can design it to be for both storage of CO2, just oil recovery, increasing that one, or both of them. With that, I'm going to stop, and thank you for your attention.
Thank you, Hamid. That was great. Let you catch your breath for a moment here, but why were you guys focused on the Eagle Ford formation? Is that because of the age of it, where it was at there, or was there another reason? Maybe that's where you had access.
So Eagle Ford, there are a couple of reasons. One is there are a lot of data available in public data available in Eagle Ford, right? But the second reason also is the Eagle Ford has a wide range of hydrocarbon types of reservoir. So you can have dry gas, gas condensate, volatile oil, or just black oil or light oil. So that helps if you want to look at different oil type, then it's the same basin, but at different depths, you have different hydrocarbon type.
Okay. And then with maybe related to that question, as we go to other shale formations, do our numbers change significantly? Do we have enough permeability differences there to change so that make you do the math all over again, or would you expect similar results?
It does. So another thing with the Eagle Ford that I want to mention is that it's really shale formation. It has low permeability, extremely low permeability. Whereas if you look at the Bakken oil, it's not shale, it's tight sand. It's
Okay.
not, and its permeability is 1 or 2 orders of magnitude higher than Eagle Ford, right? So although Bakken is called shale, but it's a tight sand sandwiched between 2 shale layers. So the oil that generated from those shale formation is pumped into or moved over the geological time into that tight sand, which has much higher permeability than the Eagle Ford. The properties are going to be different, right? But with our model, it can basically seize all of that. But the middle Bakken, I would say, is going to behave less toward what we have behavior in Eagle Ford, and more toward, let's say, carbonate reservoir, because carbonate also is tight but fractured, right? So short answer to your question is they are different, but that was the whole point of the optimization. And if you have different type of oil, we can consider that. And you can also see the recovery factor that was reported by Advanced Resources International, that they are different if you look at different. For example, the highest you see is from Bakken, right? The primary production recovery factor, right? And if the lowest you see is from Permian, which is much tighter. So this higher is because they have a higher permeability too.
Okay. Very good. Appreciate that. So I think you covered this in your presentation, but maybe this is a re-ask, but maybe this has a little different spin on it. When we're injecting that CO2, how do we, while still producing that well, how does that CO2, how are we keeping that CO2 in place? And how are you able to measure how much of that CO2 doesn't stay in place? And I think you had
So when we inject CO2, the soaking time or soaking period is basically when you shut in the well, hoping that the CO2 you injected that's now are in the fracture network, right? Hydraulic or natural fracture, they're gonna start moving into the rocks, into those pores in the matrix, right? But not all of that is going to go there, especially with shales. They are so low permeability that most of that injected CO2 is going to stay in the fracture network. And when you start producing from the same well, you produce a lot of that CO2. It's going to come out actually first, right? But not all of it, right? So still, you may produce 80% of that CO2, but then you're going to separate that CO2 again from the oil that came out of the well, right? And then re-inject that CO2 in the next cycle and add more CO2 to it perhaps, right? So you're going to have the CO2 that you injected come out, and big portion of it. But you're going to recycle that, send it back with some more CO2, and then you repeat this process 10, 20 times. And at the end of the day, you're going to have some CO2 left there because, again, the CO2, the property of that and the organic matter in shales, some of the CO2 is going to stay behind, even though you're producing back everything, because they want to stick on the rock, organic matter surfaces of the rock.
okay. And then they follow up to that follow up is then eventually, maybe 30, 40 years from now, who knows how long production lasts, then someone is going to come along and seal that into place.
So I'm going to go to that slide where if we really want to do CO2 storage, what should be the strategy, right? So here, right, so here we are doing cyclic CO2 injection, right? You can see the amount of CO2 that's now is going up. That means the amount that this is a soaking period, basically, or injection period, right? And then when you start producing, then most of the CO2 is coming out again. Then you inject more CO2, produce CO2, inject CO2, produce, inject, produce, inject, produce, then inject. And you start injecting, and it's going to go up, right? So the last cycle, you can just inject, and then injectivity is going to be going down because now the fracture network is filled. You cannot inject more because if you go more than the fracking pressure, then you may cause major fracture that goes to the next well and or somewhere that you don't want, right? But what you can do, you can shut in the well, wait a few months or a year, then start injecting more CO2, right? So if you want to just say, I'm done with this reservoir or this well, you can inject more over time and let the CO2 get into the smaller pores, but it needs time. But the only issue is that if you don't plug the well and you want to still inject maybe 6 months from now, then you have to watch for what's happened to the wellbore, right? Because it's still active well, although you shut in, but you're hoping to inject more CO2 in 6 months. So that part of it, you have to do monitoring. But in case of injecting more, you can do that. And then at some point you can say, okay, I'm going to plug in the well and move on.
And give us a time frame. I think you did. What are those time frames for those cyclic injections, and what are the time frames for the soaking phase?
So industry, when they implement this kind of process, they are into not shutting the well for such a long time because you want to produce more oil, right? If you shut in the well, that means no revenue, right? So the soaking time for example, in the scenario we consider is a month, it's actually a lot for the industry. They don't want to wait that even 1 month. They may wait a couple of weeks, right, or a week, right? And some of our analysis showed that the soaking time of 1 week versus 1 month versus even 2 months doesn't make much difference unless you give it over a year for soaking for the CO2 to go to the rock. The difference between 1 week and 2-3 months may not be much. Why? Because the CO2 that you're injecting, it needs much longer time to get into the smaller pores. So instead of doing that, you can go with a short soaking time of maybe 1 week, and that CO2 has enough time to mix with the oil in the fracture network, and also big pores and microfractures to then, when you produce from the wells, you're kind of flushing out the macropores and fracture network. But for the other part, like half time, which is the injection time, right? It depends on how much CO2 you want to inject, right? Because we're injecting with a constant rate, and there's a volume that we want to inject, right? So if the rate of injection is small, maybe the half time is going to be a little bit longer. So it's about how much volume of CO2 we want to inject. But it's around, again, a couple of weeks to a month or so. As far as the puff goes, it can be longer than half, and for sure is longer than soak. And that could be a couple of months to half a year even, right? So because that's the time you're producing oil. So the company, they don't mind more time because you're producing.
Yeah, I always like it when I get paid, Hamid.
Yes.
So we only have a few minutes left, but certainly if you have more questions, please type them into the chat, the Q&A, wherever you want to. This question is, how different is the Eagle Ford in terms of heavier hydrocarbons than Marcellus, Utica, et cetera, and that's probably depends where you're at on all those formations, but have at it.
Yeah, so Eagle Ford, as I said, if I go back to this, it has here. You can see it has different. It has gas window, oil window, for the same basin, right? The gas window is deeper, right, where you're going to have a shale layer that is mainly gas, and if you go shallower, you're going to have a layer of shale that has a lot of oil. Marcelo and Utica are dry gas mainly, but then if you go towards western PA, it became more condensate, right? But with Marcelo and Utica, you don't get more than condensate. Whereas in Eagle Ford, you have light oil and kind of black oil in terms of type of hydrocarbon. So we don't have that in Marcellus and Utica. In terms of hydrocarbon type, Marcelo and Utica, the best you get is gas condensate.
Okay, very good. I don't see any new. I'm sorry, I just can't read very well. This question, I'm just reading it for the first time. Sorry. One of the largest issues when performing gas Huff-n-Puff in the field is keeping injection gas in the same formation, same well pad, since most of these tend to leak off drilling section. Soak time does not matter. Also, there is a limit to injection rates that are achievable. So I don't know if that was a question, but great observation.
Very good point, actually. Yes.
Yeah.
I can add something here. Yes. So soak time doesn't matter, as I mentioned, because again, soak time matter in conventional reservoir, right? This Huff-n-Puff process we are adopting for what we used to do in conventional reservoir, where soak time matters because you have higher permeability. In these shales, it doesn't matter as much unless you really go long soak time that economically is not viable for companies. And the first part was about the injectivity and the interference between the injection well and other pad. That well interference and frac heat and the issue we have in terms of connection between the wells in the one pad to another one, it's there. And whatever you inject, whether it's during fracking or during EOR process, that's going to be there, and you have to really be mindful of that. That's going to cause an issue where the CO2 you're injecting may not end up going to the formation that you were hoping to go, but it's going to go to the neighboring pad.
Yeah. Very good. Last question, then we're going to let you go for the day. What impact does CO2 injection have on the gas produced from that formation? And if producers are required to conserve gas, not flare, et cetera, does that create challenge for gas processing plants?
Oh, if you're going to do CO2 Huff-n-Puff, you definitely need gas in a facility, surface facility. You need to be able to separate CO2 from the produced fluid, and that's because you're going to get a lot of CO2 produced back. So that's part of it. You have to be able to do that.
Okay.
But
Okay.
sometimes it's okay if you're going to have some methane with CO2 because methane also improves, right? Because you're going to inject back some CO2 with some impurity, which is methane. As long as it's methane, maybe it's okay. But if it goes to H2S and other things, then you don't want that.
Okay. Very good. Hey, on behalf of Penn State Extension and the TOPCORP team, University of Texas at Austin and Colorado School of Mines, we sure would like to thank you for all the efforts you put into that, Dr. Emami-Meybod. Probably got your name wrong again. Won't be the last time. Thank you again. Great webinar. Appreciate it.
You're welcome, and thanks everyone. And if anybody has any question or follow-up, you can reach out to me with my Penn State email address, emami@psu.edu.
Wonderful. Thanks again. See you, everybody. Appreciate you coming.